Anyway, so let's turn it on, the recording. So the last two topics in the Physics 442 content of the course were going to be three-dimensional motion and especially angular momentum, quantum mechanics of angular momentum, and quantum mechanics of indistinguishable identical particles. So today's lecture will touch on the first topic, and I will try to give a lecture, make a lecture and record it on the identical quantum mechanics of identical particles and post it. And the challenge is going to me at least, the challenge will be to somehow figure out how to assess that, because we're out of homeworks. I think because the final exam is going to be a take-home exam, I am going to put one problem on the final exam to sort of maybe something as small as deriving some of the details of what I'm going to talk about in class. So it's not going to be a very challenging problem, but it'll be just a problem to make sure that you guys, follow. Anyway, all right, moving right along. So we're going to be talking about angular momentum, and I thought that maybe I would take this as an opportunity to fill in a gap that we left at some point from earlier this semester when we talked about momentum. When we talked about momentum, I followed the sort of the approach of some of the basic quantum mechanics books, which kind of like give you the definition, which is h over I d by dx. Okay, and where it comes from is often sort of considered to be sort of a distraction from the getting to use it. But the basic idea with a lot of the important operators in quantum mechanics, they're related to pretty simple ideas of symmetry. So, so what momentum is, the role of momentum in the theory is to reflect the fact that the description of the universe is independent of your point of origin, right? You can basically, you can think of this, mathematically, when you are computing integrals, the integration variable itself is a dummy variable. That's what we call it. And so your description of the world should not depend on the specific choice of the dummy variable. But to do that, to check that, we kind of want to be able to transform the coordinate system. And for the for the point of for the case of momentum, we want to look at translations of the system. And translation of the system. So now instead of doing this in the classical sort of a language, I'm going to jump straight into the sort of wave function. So if we have a wave function in Hilbert space psi, we would like to translate this wave function in real space by the translation operator. Well, to do that, we have to write the wave function in real space. And the wave function in real space is written by taking the wave function and dotting it with the projector on a particular x eigenstate. Remember that we've talked about how operator x can be thought of, position x, but then there's an eigenvector x, and you project it onto, so the operator x is essentially a superposition of all projectors on position x with the weight x. But here we're talking about the wave function, so we're going to represent the wave function in the x basis, right? This is still a vector. We haven't projected anything, but we're simply representing the state of the system in the x basis. And so when in quantum mechanics we write down psi of x, what we're really talking about is this abstract psi dotted into x. Anyway, the star of this slide is actually not psi of x. It's this object. which is this mysterious translation operator operating on X. And its action is defined. It's, so far we're not computing it. And that's just defined that whatever X was here, we're going to, if you operated with T of A is the amount of translation, some length, then that gives us the eigenvector X plus A. Okay. Now, because X is a dummy variable, you can translate the dummy variable, right? So this is sort of, if we call that X prime, then we can do an integration with respect to X prime. That's what's written here. And now we're going to, and this is in principle exact, but not really manageable. So at this point, we want to consider infinitesimal translations. That's what this says, infinitesimal translations. And of course, that's where our calculus comes to the rescue. Psi of x becomes, psi of x minus a becomes psi of x minus a grad of psi of x. And so what we realize is that if we want to do infinitesimal translations, we want to take derivatives. In the position space, the representation of momentum is essentially a derivative. Now, you might at this point ask, well, how is this related to that? Why is there's this, how does this H bar even come along? And I think that the easiest way to motivate that is to say that, look, in hindsight, quantum mechanics tells us there are these phase factors, which are energy times time divided by H bar. And, to initiate a translation, we want an object that looks like, X or whatever, the translation that we're making by, I'm skipping some steps, but basically the object we want. So if you were doing differential equations, or if you were doing calculus, it turns out that if you have an operator doing infinitesimal translations, which is d by dx, the operator performing translations by a finite amount a is this guy. And indeed, you can see that in Taylor series, this is 1 plus I a d by dx, right? And so if you consider exponentials that look like this, and you sort of go back 100 years to the beginnings of quantum mechanics, you realize that, E times time and momentum times R come together in sort of relativity theory. You realize that the natural definition of momentum is, in fact, the one where H bar shows up as a coefficient of d by dx. All right. This is not a leak-proof derivation. In fact, there basically half of it was derived, half of it was imposed on you here. But this is sort of an idea that oftentimes thinking about symmetries of the problem, the fact that you really don't want to, you start solving the problem in X in some basis where there's an origin here somewhere in space, only because you have to write down a differential equation and to start cranking things out. It's not because the universe prefers your origin to somebody else's origin. And so there are these operators that sort of tell you that if you translate the problem, it won't matter. So simply, the energy of the harmonic oscillator doesn't matter if you move the harmonic oscillator left and right. Okay. Not sure if this is helpful, but I thought I'd get it out of the way. So similarly, the theory of angular momentum comes about because, if you rotate your coordinate system, now I just talked about the origin of the coordinate system, which is a translation, but if you rotate your coordinate system, if you rotate X into Y or X into a little bit away from X, again, the problem shouldn't matter. And the way this comes, again, the way this comes at you in, say, Physics 120 is quite different, of course. You find out that the kinetic energy which is our beloved p squared over 2m, for a rigid body that's rotating around the origin, some origin, can be written, can be massaged, if you really think about this sort of a rigid body made up of little masses, and if you kind of think about p squared over 2m in those terms, you can rewrite p squared over 2m as a similar looking expression, which is L squared over 2I. And L, then one starts sort of making analogies that, the quantity that keeps track of how much motion there is, just like there's a momentum, there's an angular momentum. So this is just reminding you how angular momentum shows up in Physics 120. Unfortunately, it shows up pretty late in the semester where everybody's exhausted, and it is much more complicated to wrap your head around, because it's a good question. Why, I've always wondered whether it feels very complicated because it was introduced pretty late in the game when everybody's too exhausted to really pay attention. But one peculiar thing, okay, but anyway, let's not degrade into sociology here. The thing that we learn in Physics 1, or should learn in Physics 120, is that the amount of angular momentum is not just the amount of motion, which is p. The amount of angular momentum is a convolution of sorts, product, an angular product, between the direction to the distance to the anchor of motion, the axis of motion, and p. Right? So if this thing is moving, there's a p vector and there's an r vector, which is distance from the origin to the point of the mass, and the angular momentum is r cross p. Now, the interesting thing here is that you should think about that if the units of p are h bar over I d by dx, what are the units of L? I think thinking about units in very simple physics problems is not very useful, but the moment problems get a little bit complicated, thinking about units is often a very productive thing, because you can guess what the equation should look like without remembering them. So in this case, anybody want to venture a guess what the units of L are? Anybody? We're talking about classical mechanics. We haven't touched on anything quantum yet. So if the definition is r cross p and the units of p are h bar, if p is h bar d by dx, what are the units of p? Let's talk about that. I mean, I can start calling people out if that helps. I don't know. I know Rucaldo always pays attention. Rucaldo, do you know what the units of a momentum are?
No, not really.
Well, so if I give you some quantity A, and this quantity is made up of two other quantities, B and C, I think the easy, remember one of these sort of tricks that kids learn, when somebody asks a question, it's okay to give some answer, right? It's, what's the color of A? Well, it's not the color of B. So in this case, the units of A are the units of B divided by units of C, right? So in this case, the units of momentum are the units of h bar divided by the units of dx, but the units of dx are length, right?
Right.
So all I was trying to get out of this sort of a wake-up question is that the units of, if the units of p are the units of h bar, whatever they are, they could be complicated, divided by length, the units of angular momentum, even though there's a cross product, it's still a length times p, right? Length times p. That means that the units of angular momentum, even before we go to quantum mechanics or anything, are h bar. Okay, so h bar is this weird thing that showed up pretty early in the quantum theory, and many people have latched onto it in the sense that if there's anything that has units of h bar, it might have an interesting image in the quantum theory. And so it turns out that the classical angular momentum, without doing any quantum mechanics, already has the units of the most fundamental sort of a quantum thing, which is h bar. And so partly because of this, it's not, look, the point is that there was one mysterious thing in the theory of angular momentum, which was an accidental discovery of spin, which is the internal angular momentum. I'll say, we've already heard about this on and off. And the point is that fundamentally, the reason why this was allowed to happen was because angular momentum itself, without quantum mechanics getting involved, already has the right units, okay, roughly speaking. But anyway, this is sort of a cultural, extra cultural thing that you should always think about units, especially when things start getting complicated. And to my mind, angular momentum is when things start getting complicated in physics 120, okay? In elementary classical mechanics, once you start getting to rotations, that's where things are starting to get really interesting. Okay, so the big driver for developing what I'm hopefully going to discuss the rest of the class, it was understanding the atomic structure of matter, like hydrogen, right? So there were very precise experiments observing that there are states inside the hydrogen of electron, and they knew there was electron because you could excite it with light. There are states inside the hydrogen which obeyed a certain regularity. If you like, again, since there are so many, historical sort of significance. There's so much historical significance to a lot of these things. You can think about the way Newton came up with the model of the solar system, right? So there were several models of the solar system before Newton. And Newton, famously, people talked about him standing on the shoulders of giants, of Galileo, of other people who tried to understand the solar system. The whole idea was to understand. So what motivated Newton were empirical observations by Kepler, and based on, again, experimental, astronomical data of predecessors. That observed certain regularities in the motion of planets, that there were the 3 Kepler laws and stuff like this. So the thing that motivated, very precise, very careful look at all of this was the fact that there were oops, didn't mean to fast forward, whoops, wrong way. There were spectra of hydrogen that follow a certain pattern. For example, the energies that you could of light as it was coming out was following. There were certain transitions in you could excite the atom to go from one state to another, and it was observed that the energies, the frequencies, so this is going back to Daniel's question, whenever you excite things, what you end up observing is difference in energies. And so and that shows up as frequencies of vibration. So the hydrogen atom could be made to vibrate, and there were very, very precise measurements that indicated that the law that they followed was this 1/n² law, where n's are integers, right? And so in a way that the story mirrored what happened to, the solar system with Newton and everybody, except with a big difference. The big difference was that at the times of Newton, every step of progress, every breakthrough took 100 years. Here, everything happened in 10 years or 20 years, okay? And so the big sort of progress here is that, that one could understand the structure of the hydrogen atom in a lot of detail. There were quantum numbers, which is all of these lines could be characterized as with integers, 1, 2, 3, and so on and so forth. And then there were additional integers, and this is what we're going to focus on today. It turns out there's a finite structure which was difficult to understand without understanding quantum mechanics, the quantum mechanics of momentum. And all of this is, well, okay, since I have slides on this, let me just keep going. So this was a big triumph for, sorry, this is, I should explain. I was having a hard time, drawing circular quasi-orbits around hydrogen. So I decided that since there was a grid here on my slides, I would draw electrons going around in square orbits, which is of course not the case. But I think one of the motivations for this was the understanding that without quantum mechanics, hydrogen would be unstable. It was kind of like do or die challenge to explain it. All right, so there are two preliminary steps. Now we're going to try to pretend that we don't know what's going on, which most of us don't at this point, and we need to think about the hydrogen as a nucleus which is big and positive, and electrons, or one electron because it's hydrogen, which is light and negative. And there are two important steps. One of them is the reduction to the, actually wait, these slides are jumping around too much. Okay, right, so there are two preliminary steps. And one of them is, say if you wanted to understand all of the elements, then we'd have a problem of the mating electron, because electrons are actually strongly repulsive. And it turns out that that's a very difficult problem, and it vexes us to present day. I think we don't even understand helium that well, except numerically. Other elements, I think, given the amount of time that elapsed, we have pretty efficient schemes for approximating what's going on, but nothing at the level of what we can do for hydrogen, where there's only one electron. So generally, I think the upshot is that molecules and higher elements are hard, but hydrogen is remarkably easy. So the first step is ignore other electrons. And that's not a good approximation. So the idea is that, okay, because we're physicists, we want to kind of understand something really precisely. Let's ignore the problems where there are other electrons. Let's just focus on hydrogen where there are no other electrons. The other problem is that there's still not one electron. There's one electron in a nucleus. Turns out this problem is easily solved. And this goes back to the idea of translational invariance, because when you have translational invariance, there's a notion of the center of mass and relative coordinates. And for just two particles, the nucleus and the electron, the decomposition for the center of mass and relative coordinates is easy to write down. It's right here. These are just formulas that we have seen in Physics 120. Well, you probably have seen it more recently than I have, since I haven't taught Physics 120 in 5 or 6 years. And the important thing is that there are certain things that are exact about this transformation, right? So the idea is that there's R1 and R2. Let's make R1 to be a nucleus, R2 to be the electron. You can transform into a coordinate capital R and a coordinate little r. And the idea is that there is a, in principle, if this thing is light, what we imagine is that there's a system where, this is R1 and this is R2. But then there is a center of mass, which is R, and then there is a relative coordinate, which is R. And what we want is, as I say on the next slide, in the limit where one of the masses is really heavy, what will happen is that for the most part, the lighter one will be whizzing around and doing interesting things, whereas this one will be like almost an anchor for this problem. So I think it's actually a good approximation to say that, the ratio of M1 to M1 plus M2 is approximately 1. So the nucleus is very heavy. The nucleus is approximately 1,000 times heavier than the electron. But it turns out that none of that is necessary, because if you think of the kinetic energy, which is p squared over 2m, you can exactly separate it into little p squared and capital P squared. So that's good. That's an exact statement. So you don't need approximations of one thing being heavier than others. Importantly, the interactions only depend on the difference on the distance. It's an electrostatic interaction. If you put an atom into an external field, this would be wrong, and this separation would be useless. But an atom in vacuum is described this way, and so you can see that there's a reduction to a relative coordinate problem and a center of mass problem. And just to finish it off, one can establish that these two sets of coordinates, the center of mass coordinate and the relative coordinate, they commute. So the punchline is that the exact solution of this problem is a product. So if you have two sets of things that sort of don't see each other, and the Hamiltonian is the sum of them, it's as if like you had, you and your friend had problems to solve, but you didn't know about each other. So you solve your problems independently. Then the universe says, oh, wait a minute, there's this thing going on and there's that thing going on, but they're independent. And in classical differential equations, that's called separability, separation of variables. And if you have separability, the solution is just a product of two things. Let me make a little remark here quantum mechanically, because we are interested in quantum mechanics. Quantum mechanically, this has an obvious sort of a consequence, that if you think of the probability distributions in separable problems, right, they will look like probability distribution of one component of the problem, in this case center of mass, because now I'm talking about squaring this. If you imagine squaring this, quite trivially, the fact that the wave function is a product of a wave function, that means that the probabilities will be a product of probabilities. And so you can see that the quantum formal, the quantum description of a separable problem is essentially a statement that the probabilities are uncorrelated. So that means that there's no conditional probabilities between the two sets of problems. Anyway, it's relatively sort of a natural here, but let me just advance. Okay, as I promised, we're going to flesh out the following structure here, which is the angular momentum operator, which we'll define shortly, has certain properties that very closely resemble those of the harmonic oscillator ladder. So there's a discrete set of states, and we can go from one state to another with raising and lowering operators, and we can count all of these things. And that sort of provides for us this armature with which we can solve the three-dimensional Schrodinger equation, and I'll briefly mention that hopefully. All right, so let's now roll up our sleeves and start writing operators. Right, there isn't much mystery. Once you know what operators are, composite operators is just like two operators in series, right? So the angular momentum vector, let me just emphasize that, it has three components, x, y, and z in 3 dimensions. You can open up the R and P and write them out in the coordinate the coordinate representation, which is say that px is going to be h over I d by dx, and so on and so forth. and you get to that. So now you start, okay, now you know the answer to this question. The units of L are h bar, and you can see that, you know, y and d by dz have the same units, they cancel. Okay. Now, here's the first interesting point. This is just a quick reminder that x and p have a commutator, which is h bar, right? The same is true for y and py and z and pz, but importantly, cross commutators vanish, right? So we know this. So all of this is just a quick review. Now let's consider commutators of Lx and Ly. And, you know, again, none of this is strictly speaking quantum mechanics. The idea is you can think of, the moment you think of L's as generators of rotations, so Lz, right? So a rotation around z hat by phi is e to the I Lz phi. Okay. So this is a rotation matrix in classical coordinate system, right? It'll also be a rotation matrix on a quantum wave function in three-dimensional space, okay? But because of what we know about rotations, if you rotate around Lz and then you rotate around Ly, you're not going to get to the same place if you rotate around Ly and you rotate around Lz, right? You can, again, the funny thing about, you know, these statements is that if you've played around with tops, if you got like three-dimensional sort of a imagination based on your whatever, you know, sports activities and whatnot, then this is an obvious truth. Those of us who are less intuitive about these things have to do some math. The math is unpleasant, it's right here. So, you know, to actually think of, so right, what I was trying to say is that whilst it might be obvious for finite rotations, it's really about the infinitesimal, you know, we want to start with very small rotations and relate this to properties of commutators. And so to do this, you can just expand this out. And using these sort of relationships, you can simplify, right? Simplify what I meant to do, sorry. Do something really quite beautiful. You know, this is ugly, but this is beautiful. In fact, all right. Wow. Okay. And it turns out that there is this very complete circular pattern of commutators. So Lx with Ly is ILZ. In fact, you know, those of you who remember your Calc 3, I assume you learned this in Calc 3. It's I epsilon. Maybe I'll use. So the general formula for this, of course, is used. You can write it with the Levi-Civita symbol. It's I LC, this sort of thing. It's called. I don't know if you've seen it. I guess I could pause and ask, but anyway, let's continue. So this is really important. This establishes the rules on motion on a sphere, right? So the idea somehow is that when we talk about rotations, we're not talking about changing the distance to the origin, we're just changing the angular position. And that's what would happen is that if you sat on the surface of a sphere and you just moved around, say, you know, when we go from, you know, Staten Island to Manhattan, or from Staten Island to Venice, Italy, and we're moving on the surface, and that's, you know. Anyway, the important thing is that anytime there's a commutator, there's a statement, there's an uncertainty principle, and this is sort of the general sort of idea. If there's a commutator between A and B that's not zero, the expectation value of the commutator tells you what is the smallest uncertainty you can have mutually on A and B, right? So if you try to create a, say, for example, from X and P commutator, you know that if you try to put a particle at the origin with absolute certainty, then its momentum is absolutely uncertain. Right? It's one of these things that you have to balance uncertainty. Now, in the same sense that you cannot specify at the same time position and momentum, that also means that you cannot specify which way the angular momentum is pointing. So that means that if you spin a top, right? So classically, you can say that, okay, I have a, let's say there's a dreidel spinning it. So you would say the angular momentum is pointing up. So L is equal to LZ, Z hat. And the fact that the commutators, they're commutators, means that no matter what you do, there will always be some uncertainty, i.e. wobble. Quantum wobble. Okay. All right, let's continue. Let's do some more commutators. So this is sort of a general thing, but the important result for the next calculation is that there are these commutators among Lx and Ly and Lz. Okay. So now we're going to play the following game. We're going to define Ly from Lx and Ly. We're going to define L plus and L minus, and you're going to start. Oh, come on. Right. So first of all, you're going to see that whilst Lx and Ly don't commute, L squared commutes with all of them. X, so L squared also commutes with Ly, also commutes with, basically commutes with all of them. Okay. That means that you can specify L squared and Ly simultaneously, or Lz. So again, this might be hard to wrap your head around. I'm not going to try to give you intuition on this for now, because I don't really. I try not to think about some of these things intuitively, because it's kind of like a narrow path of before you start being unhelpful. So I think for now, let's just stick to math, okay? And we're going to define these L plus and L minus because they will turn into raising and lowering operators similar to A and A dagger for the harmonic oscillator. And for now, the result that we need is this result. LZ commutator with L plus is H bar L plus, okay? So now you notice that this is not LZ. So you can see that we effectively, by defining L plus and minus with Lx and Ly, we broke the symmetry. We said that Z is special. So everything is going to be done along Z now. Now, that's just a choice, right? Because we could have chosen X and then made up L plus and minus with Z and Y, for instance. But this is sort of another example that sometimes there's a complete symmetry in the problem, but to make progress, you have to break the symmetry and just pull things apart, okay? And so here, what you see is that once you've done that and defined these L plus and minus, you can see that the LZ and L plus and minus have this interesting relationship. Now, this might remind you, so you remember that in the theory of the harmonic oscillator, we defined A dagger A, and we had this relationship that n hat A is A, for example. A or A dagger, sorry. Yeah, A, for instance. Now, this is similar, but not quite. One of the things that should immediately stand out at you, and I'm going to hammer this point, is that there is an H bar which has units. And that's because A was dimensionless. A is dimensionless, but L is not. And you can see that on the left-hand side, there are 2 powers of L. On the right-hand side, there is 1 power of L. So you have to soak up the dimension with an H bar. Okay. That's one difference. Okay, so L minus has a similar sort of a story with LZ. Okay. And so what you see is that, okay, already you can see that LZ might play the role of the counting operator. Okay. So in the same way with the harmonic oscillator, you had, n was an integer, essentially on eigenstates. You'll see that LZ, we'll use LZ to label eigenstates as integers. Oops, something just happened to my screen. There we go. Okay, there we go. So let's use this property as we did before. So this is the commutator, but now unwrapped, right? So with the commutator that we were looking at just here, actually, maybe I should stop and see if there's any questions. Any questions? I'm just going through equations at this point. I already told you where I'm going. I would like to get a, I would like to derive in the same way that for the theory of the harmonic oscillator, we derived with no differential equations whatsoever, with just commutators. We derived that there's a ladder of states, and we can go up and down this ladder, and these states are eigenstates of the harmonic oscillator Hamiltonian. Here, what we're doing is slightly different physically, but the same math. Physically, what we're going to see is that the eigenvalues of L squared can be arranged in this ladder of LZ states. And there will be essentially identical set of protocols for going up and down this ladder. In other words, we will never have to compute eigenfunctions all at once. We will just sort of step them up and down. Look, the idea is basically to take this trick that worked so well for the harmonic oscillator and use it again here. And there are a couple of small changes, but it's mostly the same trick. Okay, let's get back to this PowerPoint thing. Okay. Where was I? Oh, how am I doing in chat? Oops, I better hurry up. Okay. Right. So just as with the harmonic oscillator, once we got the commutator figured out, we now imagine, now we kind of like open up this commutator and observe that, L plus operating, and basically we're going to operate with this commutator on some putative eigenstate of LZ. So L plus operating on an eigenstate, and now since we assume that this is an eigenstate of LZ with some eigenvalue HM, you can see that what we've done here is we've incremented, right? We basically taken HM and boosted it to HM plus 1. Whoops. By operating on it with this combination. So with this combination, this is what L plus does. It changes the eigenvalue of psi by 1. Okay. Now, at this point, so far this is what we've done for the harmonic oscillator. Now we're going to do something different. And the different thing here is that the harmonic oscillator did not have the analog of L squared. L squared is a positive operator. The eigenvalues of L squared have to be positive. Now what we notice is that we can replace LZ squared with M squared. Right? Now we imagine operating on some side just like that. And because these are positive, right? This basically tells us that L squared, is bounded by M in this way. That's trivial. And that basically tells you that whatever the maximum values, whatever the maximum values of and minimum values of M are, basically if L squared is a bounded operator, M has to be bounded. M cannot be infinite. Right? Sorry, why it's doing this. Right. So now we're going to play the same game as with the harmonic oscillator. We're going to try to find these M's by saying that, okay, there's a ground state of this line. So in the harmonic oscillator, basically said that A's and A daggers were raising and lowering operators. What happens when you try to lower the ground state? You annihilate it, you kill it. That's the annihilation operator. Okay. Sorry, the other way around. So this is analogous to A operating on the ground state of the harmonic oscillator and giving you a 0. Okay. So this is exactly what happens to the harmonic oscillator. What happens in the harmonic oscillator, there is no highest state. There's an infinite ladder. So this does not happen in the harmonic oscillator. But because we have this very sort of a different situation here where M squared is bounded, we actually have the ladder which is terminated at both ends. Okay. And this is what we want to figure out now. And again, we're going to play the same game. We're going to now take these plus minus operators, right? And we're going to try to relate it to the L squared and LZ. Okay, it's a little bit of massaging math. So this is the answer we want. Well, actually, no, I'll take it back. This is the answer we want. Turns out that L plus and L minus, which are these raising and lowering operators, can be related directly to L squared, conveniently with LZ's already in there, so it's easy. And now we're gonna, so these are sort of in some sense, these are definitions of highest and lowest states. Actually, you know what? Maybe I should just say that, I know some of you have something else after the class. Because I'm recording, I'm just going to keep talking until I run out of slides. If you need to sign off, don't worry about it. I mean, I can't even see you anyway. Okay, so I'm just gonna I'm gonna ignore the fact that we scheduled this until 10. I'm just gonna keep talking. I apologize for that, but since it's recorded, I don't feel so bad. Okay, right. So these are definitions of what the top and the bottom of the ladder are, and now we want to exploit those definitions to gain some information about the eigenvalues. So the idea now is that this is exact as obtained from that. And now we're going to ask, what happens if you take that and operate it on the highest state or the lowest state? Okay. Now the highest state, and obviously the thing that we're trying to exploit is that the fact that L minus and L plus is very complicated generally, except when it operates on H max, psi max, which is just, it annihilates, it gives you 0. Whoops. No way. Am I missing a slide? No. All right, right. So if you consider this, and then, okay, I'm just gonna stop talking and start underlining things, right? This one basically just drops out, and you end up with sort of a very simple expression. Come on, what's happening? Right? because LZ squared and LZ are simple, M squared and M max, M max squared and M max themselves. And so what you gain out of this is that L squared operating on this highest representation state is just H squared M max plus 1. You can repeat this trick and you will get, you can repeat this trick on the minimum M min state, and everything is going to look the same, except we're already sort of M min is going to be something negative and, some other thing. But because, remember again, that L squared and LZ commuted, that means that, we're actually computing the same quantity. That means that L squared operating on any of the M states is the same. Right. And that gives us this equation. Okay. And from here, we can deduce that M max and M min are just related. They're basically the same thing up to a sign. And we can count the total number of states. Okay. Now, at this point, I think it was Paul Dirac, who realized that, wait a minute, what is the constraint here? The constraint is that this is an integer. In other words, when we count things, we should get whole numbers, whole positive numbers, whole number, aka integer. Okay. And so one way to get an integer is to say that L is an integer. But L can also be half, 3/2, and so on and so forth. And so it turns out we're not gonna get a chance to get into this. It turns out that these were the only ones that were kind of expected. And for physical reasons, these are the solutions that can be connected to real space rotations. And these were spurious, and they were not, they were believed to be just some artifacts of the theory. But it turns out that that's not the case. If I remember correctly, Dirac predicted them simply based on the mathematics, and they were discovered later, but I could be wrong. I could have it exactly backwards at this point. I'm not. I don't remember the chronology, whether they were discovered and Dirac explained them this way. It's a little bit embarrassing, I should know this, but I don't remember. So this is called spin. And the point is that this mathematics, without any good reason other than being, internally somehow lucky, consistently lucky, I'm sure, it predicted a property of atomic particles, electron in particular, that it has this internal notion of rotation. It's like a spinning top, right? So it's like, think of it, of the idea, which is wrong, but that's where the name comes from, is that an electron can be thought of as a tiny spinning top, and it spins, and its angular momentum is h bar over 2. Anyway, exciting time. All right, so I think this is basically a lightning speed crash course in quantum theory of angular momentum. It's a bit of a funny sort of a subject, and you can tell this by looking in some sort of books. So this is how the subject is generally presented in sort of old-fashioned quantum mechanics books, and that's what I wanted to follow. If you look at McIntyre's book, for example, which I like quite a bit, some of these steps were not there, and I think it's a little mystery to me why not make strong sort of a use of the analogy with the harmonic oscillator. And I think part of the reason is because it's a little bit dry and algebraic and math, and maybe that's not in vogue anymore, but I'm not sure. So I think, in the defense of the historical sort of sequence of steps of how I've been taught, for example, this is, it's just so, case open and shut. You can basically just look at these commutators, think about implications of these sort of raising and lowering operators, and before you know it, you're done. Okay. Now, the really messy thing, which, again, this is how all of this feeds into the Schrodinger equation. And unfortunately, many books only derive the angular momentum after, suffering through the Schrodinger equation. And I think the right way to do this is to first think about angular momentum in its own right, and then do the Schrodinger equation. I think McIntyre's book actually is really good at that. It's just their treatment, his treatment of angular momentum is a little bit, disconnected in parts. But anyway, now finally, to close the arc of the story here, is that now we want to go back to defining and thinking about the Schrodinger equation of the three-dimensional single particle quantum mechanics. What that means is that this is, what used to be px squared plus py squared plus pz squared is now written as p squared, where p is h bar over I grad. So this, what you see here, is really p squared over 2n. For some reason they use mu. I think I got this. I cut and pasted this from McIntyre's book, so for some reason they use mu. Anyway, the real nightmare of dealing with three dimensions is that all the derivatives don't commute, right? Basically, all the derivatives also come with extra sort of factors of 1 over r sine theta and so on and so forth. Basically, and this again comes back to the point that angular variables do not have dimensions of length; they're dimensionless, and so your dimensions of length have to come from radius. Anyway, since all of you have had Calc 3, you should remember this, or at least you should remember that this thing exists. Most people do not remember this, but I want somehow that it does exist. So operating with, so this is a vector, right? This is a grad dot with itself, right? So it's a scalar at this point, but because there's a bunch of derivatives, you have to be careful with how you propagate the derivatives through and collect the terms, and this is what you end up with. Okay, and so the horrible task at hand is to solve this differential equation. And now you might ask, why do we bother with spherical coordinates? Why don't we use Cartesian coordinates? And the answer is that V of r depends on separation in real space, and that horribly mixes. So it's a V of square root x1 minus x2 y1 minus y2 plus z1 minus z2, and so you can see very clearly, whereas the kinetic energy part is nicely separated in Cartesian coordinates, the interaction part, the potential part mixes, or rather couples, x, y, and z. So it's hopeless. So you have to look for a better coordinate system. And and ultimately this is what Newton had to do for the solar system. Right? This is why in Physics 120 we talk about circular motion. all of that centripetal acceleration, all that stuff comes because you changed the coordinate system. And now we have to do quantum mechanics on that. Okay, so you might have walked away with the idea from the first half of this presentation that, oh, you understand quantum mechanics of angular momentum, and that would be true, but you understand it algebraically. Algebraically usually means, just like, so I'll give you an analogy. So there's a when you think about space, there are geometric properties of space and there are topological properties of space. So geometry is the thing that talks about distances, and topology is the part of the geometry, is the part of real space sort of properties that doesn't talk about distances. For example, if you have a loop, right? If you can go to the same between two destinations by two different paths, then you have a loop in your parameter space, in your configuration space. You can have multiple loops. So topology keeps tracks of loops, whereas geometry keeps tracks of your coordinates. So similarly, in some sense, algebra, not the high school algebra, but when you talk about operators and when you talk about objects abstractly, you don't talk about representation of that operator in some space. You talk about their relationships. So when we talk about commutators, even though we derive them oftentimes by writing x and d by dx or writing out matrices, the notion of a commutator is more general. Right? So now, in order to break it all down and start solving the three-dimensional Schrodinger equation, we have to write the angular momentum in some set of variables. Okay, so you can see that LZ actually has a very pretty representation in spherical coordinates. It's IH bar d by d phi. That's a simple derivative. H bar just soaks up the dimension. There's a reason why I did not write Lx and Ly. They're more complicated. L squared is already horrendous. But you start noticing something really beautiful here. The beautiful thing here is that no R, right? So that means that any problem that involves L's is a problem of a motion on some rigid sphere where you're not changing the distance to the origin, right? And so what turns out to be the case, and maybe I should back up so you can see it. So if you take the del squared, you notice that there's a portion here that depends on R only. And there's a portion here that has a peculiar property that R sits outside and has no derivatives, nothing. It just has 1 over R squared. Okay. And you can see it. So it turns out that the coefficient of 1 over R squared is L squared. So it turns out this is none other our beloved L squared over 2I. Right? Remember that I was, for a point particle, was mr squared. So you can start connecting the dots here, right? H bar will cancel. And so you can see without too much extra work that, when you write down p squared over 2m for a three-dimensional motion, there's going to be radial motion, roughly speaking, pr squared over 2m. And then there's going to be angular motion, which is correctly written as L squared over 2I. Okay. So this is the centrifugal barrier, it's called. There's extra kinetic energy if you want to move in an angular fashion. So this is actually very simple and very pretty, I think. Oh, there's only 2 people left. Okay. No, but as I said, I'm almost done, but let me continue. So this is actually a very simple point, that you can take the Schrodinger equation and you can take the kinetic energy and you can pull it apart into radial and angular thing. But then you realize something even nicer that, whoops, that the interaction energy only depends on the separation, and it does not depend on theta and phi. And that means that the angular momentum problem, the circle, or the problem that involves, theta and phi, actually does not depend on this at all. And so what that means is that the problem is completely separable. And the full wave function R of theta, psi of R, theta, and phi can be written as the piece that depends on R and the piece that only depends on the angles. Okay. Oops. Okay. And right, and so the point is that the energy from the angular motion only shows up as a coefficient of 1 over R squared. So the answer is that you have to first solve the angular momentum problem and then replace this with L plus 1, as we'll see on the next slide. Right here, this is L squared. So, by first figuring out the spectrum of L squared, what we've done is that we've broken up this three-dimensional problem into two steps that have a one-way relationship. That LL plus 1 is determined ahead of time. You stick it into here and you try to solve for this problem. And ultimately what you're trying to get out of these energies. Now, what you see is that this is a one-dimensional problem versus R. You can think of it as a one-dimensional problem moving in this potential, where the amount of motion, angular motion comes in as a 1 over R squared potential. It's again, you can think of it as a quantum Coriolis force. I don't know if you guys have ever heard of the Coriolis force. So this potential is funny, it blows up at the origin. It means that if you want to move around, if the electron wants to move around faster or around the nucleus, it has to actually move further away, right? So you already have some experience with quantum mechanical problems that you basically just want to go and sit in the minimum, roughly speaking. And you can see that because of this 1 over R squared, you're getting pushed away from the origin, which is, the nucleus is sitting at the origin. All right. Oops, I think I'm close to the end. All right, now let's just plug in everything, right? So this is the electrostatic potential. Z is the nucleus charge, which is 1 for hydrogen. And the upshot here, and I'm not going to discuss it, is that it turns out that this is a famous differential equation, Legendre something or other, and it has solutions only for a set of, it has solutions with the right boundary conditions, I should say, because we're talking about differential equations. Boundary conditions are key. These are the energies. So these energies, so this is 0. You can see that the 0 of energy is important. And this is n equals 1. This is n equals 2 because it's 1 over n squared, and then they just kind of crowd in like this. Now, these are all bound states, so they all have negative energies. Of course, if you manage to excite an atom so that the electron, you can strip away the electron, this is sort of a free electron states. And as you might imagine, the free electron states are mostly far away from the electrons, so from the atom. So all of this stuff is basically negligible. Free electron states are plane waves, and for that we don't need any of this machinery. We can just think of p squared over 2m. So free electron states have a positive energy, which is p squared over 2m. That's not really interesting. The interesting thing are these bound states, because what you know is that if you try to excite from this bound state up, its energy is going to be, this expression. If you try to excite from this bound state to another bound state, then there's going to be difference of n squareds and so on and so forth. And so, long story short, the entire spectrum of the hydrogen atom can be understood with this somewhat intricate hierarchy of integers. And that was sort of an enormous triumph of early quantum mechanics. Okay. Sorry about running 20 minutes over time. You guys still awake?
Yep,
Live?
still here, Professor.
All right. Okay, so I think, like I said, my challenge will be to kind of supplement this lecture with a couple of sort of reinforcement problems where I'll tell you to go into I'll share these slides, of course. I'll ask you to go and derive something that I might have glossed over. And that's the plan. All right, but please, there's a homework, I guess homework 8 for 442 students. So please try to advance on it before next Monday and ask me questions and stuff.
All right. Yeah, I'm actually working on it.
Yep, sounds good.
And you mentioned something about the final. When is the final? I know you said the last day of class is Monday. So when is the final?
What I plan to do is work on the final over the weekend. The final will be, I want to say, similar to the homeworks. And the question is, the question is that what's the purpose of the final? Okay, and considering that I have not managed to grade and return the homeworks, considering that we have not had a midterm, I think the purpose of the final that I'm thinking is fair to you guys would be to give you a review, to basically get you to review some of the things that I consider to be important from the class. Okay,
Right.
so it'll be so you should think of the final as no more difficult than a homework, but it will be comprehensive.
Right.
And what I'll do is that I'll give it out over the weekend, and we'll say that it's due in a week.
Okay? Oh, okay. That makes more sense for me because, like I told you, I'm having a surgery this Friday, so that's what I asked you.
Obviously, look, if you come back from the surgery all, energetic and they pump you full of like energy drinks, whatever. If you want to work on it, that's fine. If you want to take time off, I think the final grades are not due until graduation, essentially.
Right.
And even if you want to take an incomplete, that's fine. Look, you've been on top of everything. I have no problems. The people I have problems with incompletes are the people who haven't turned in anything. And then they come somehow they try to catch up after the class is over. But in your case, you actually have turned in everything, most of things, right? So in that case, we can just discuss what it is exactly we're talking about as far as incomplete. If it's just finishing the final, that's fine.
Oh, okay.
I'll just give you the grade whenever you can get it in.
Yeah. All right. So yeah, I guess it's actually pretty fair since you're gonna give us time to do the final. So I'm gonna try to
Yeah, you might be able to look, depending on I don't know how severe the surgery is going to be. So if you come back and you take a couple of days and you're feeling like you can think straight, because I remember when I had my wrist surgery, I was on painkillers for long enough that I felt like pretty disoriented.
Yeah. But I mean, so once you post the final, I see it, and
yeah,
I'm gonna try to work on it if I feel a little bit